So the last time we connected, we were thinking about electron configurations for atoms. But I want you to think now about ions. So we looked at an example of a fluoride anion last time. But when an anion or a cation is formed, electrons are either lost or gained. So take a moment, refresh your recollection. If it's an anion, is it gaining electrons or losing electrons? If it's a cation, is it gaining electrons or losing electrons? So our focus is going to be on electrons in the highest principal energy level. We're going to consider that these ions are isoelectronic with each other. That means they have the same electron configuration type, just a different energy level. So for example, if we're thinking about the brackets that we would use for our short configuration, that might be something that would help us as we're thinking about how to set these up. So the transition metals to the right of the scandium subgroup don't form ions with noble gas configurations. So when transition metal atoms form positive ions, we remove electrons from the sublevel of the highest principal quantum number first. So in other words, when transition metal atoms form positive ions, the outer s electrons are lost first. So for example, if I have manganese, I'm going to lose the 4s2 electrons first if I was forming Mn plus 2. When I'm forming ions, the big idea here is that it's the outermost electrons that are removed. So in the case of sodium, the outermost electron is this one lonely valence electron that's on the outside. That gets removed to form sodium plus. The loss of that electron is what gives sodium a positive charge. I could also, though, represent this as the square bracket neon, because that's the electron configuration for neon. So if I lost an electron to form sodium plus, it would have the same electron configuration as neon. So let's talk about valence electrons. These are the highest energy electrons in an atom, and they participate in chemical reactions. So these are the electrons that we're really interested in, because that is where our chemical reactivity comes from. So for main group elements, the valence electrons are the electrons that have the highest n number. But for transition metals, the valence electrons also include the highest energy d orbital electrons. So transition metals have more valence electrons than main group elements. So one of the consequences of Hund's rule is that within a given sublevel, so P, D, or F, there are as many half-filled orbitals as possible because our electrons want to be alone. They want to have the farthest spread possible. So these electrons are what we often refer to as unpaired. The number of unpaired electrons in an atom can be measured by an experiment. If you place the substance in a magnetic field, if the substance is attracted to the field, then it should contain unpaired electrons, and it is said to be paramagnetic. If the substance is slightly repelled by this field, then it contains only paired electrons, and it is said to be diamagnetic. So our unpaired electrons are paramagnetic. That means they're attracted to a magnetic field. This is the reason why iron is attracted to magnets. So if we think about it, our 3d orbital and our 4s orbital, right? We see these single or unpaired electrons, and that's the reason why iron is paramagnetic. So what about iron 2+ and iron 3+? So if we were to draw out the electron configuration for iron, go ahead and take a moment and do that. You should be able to use your periodic table to write out the electron configuration for iron. For now, go ahead and do both the long and the short because that's good practice. Notice you can always check your work because the sum of the superscripts are these numbers that are up here, should be equal to the atomic number of the atom. So in this case, iron. So if I thought about iron 2+, that would be an ion that has lost 2 electrons. it's going to lose the 2 electrons from 4s2. So its electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. So we're going to take the electrons from the outermost shell, in this case 4s2 is the outermost shell, and then we're going to take electrons from the 3d shell. So if I formed iron 3+, I would take one more electron from the 3d5. And then this is the short configuration of iron 3+. So will main group ions respond to a magnetic field? Well, the best way for you to answer that question is to go ahead and draw an orbital diagram or to write out the electron configuration. So take a moment, practice writing your electron configurations and drawing your orbital diagrams to make sense of whether or not these ions will respond to a magnetic field. When we're thinking about elements that form ions and their charges, we know that main group elements tend to gain or lose valence electrons to form ions that are isoelectronic with the nearest noble gas configuration. So for example, lithium is isoelectronic, right, as the ion with helium. If we think about N3 minus, O2 minus, F minus, right, as well as Na plus and Mg2 plus and Al3 plus, they're going to be isoelectronic with neon. S2 minus, Cl minus, K plus, and Ca2 plus are going to be isoelectronic with argon, and so forth. So one of the really cool parts now of your periodic table is that you can look at that periodic table and know what the ions are and what their electron configuration would be simply by looking at your noble gas configurations. So here's some great practice. As a reminder, let's go back and take a look at fluoride again. So we're going to write the electron configuration for fluoride, 1s2, 2s2, 2p6. And we're going to check to figure out which noble gas matches that configuration. So if I'm looking at my periodic table, I have found that neon matches that electron configuration. The same thing is true for sodium plus. Its electron configuration is also 1s2, 2s2, 2p6. So F minus and Na plus are isoelectronic, where they have the same electron configuration. So if you're wondering, well, how does that work? Well, in the case of F minus, the electrons are added to the first available orbital. And in the case of sodium plus, the electrons are lost from the highest N first. Then, right, from P, and then orbitals before S before D. So this is a great way to think about how we take electrons away in order to form cations. The next time we talk, we're going to use everything we know to make sense of periodic properties. So we're going to take our electron configurations, our energy distributions from orbital diagrams, and we're going to start to use those pieces of information to make sense of our periodic trends and properties. You're probably wondering what discussion is going to be like. So we're going to have a great opportunity to be able to practice and showcase how you solve problems so that your colleagues can understand and appreciate the strategies and approaches you use to make sense of these types of problems. I know this is something that we talk about in class, but I really want to make sure that you're carving out time to do this. So instead of us doing this in class together on Monday, I'd like for you to take 5 minutes and organize your goals, think about your thinking in terms of chapter 6, and reflect on your learning. This is a great strategy to keep in your notebook as a way of revisiting and making sense of new knowledge. It's a great opportunity for you to ask yourself questions like, do I really get this idea? Could I explain it to a friend? Do I need more information or knowledge, or do I need more practice? So we are still in chapter 6 for this week. Then you'll have spring break, and then you'll have exam 2. More information coming with your prospects exam, and I look forward to talking to you soon. Have a great one.